how's it going? My name is Josh Panfil. I'm a fellow in the Society of Actuaries. I live in Chicago, Illinois, in the United States. In my day job, I work as an actuary and a predictive modeler working on insurance products. I use R nearly every day for all my work, and I've been working with it for several years now. Today in this presentation, I will give an introduction to R functions. We'll start off with the basics, and as we go along, we'll get into more complex topics later. As mentioned in the syllabus, a lot of this information will be coming from R for Data Science by Wickham, but I'll also be referencing R in a Nutshell by Adler. So we'll start with the most basic question. What are functions? The technical definition is that R functions are the R objects that evaluate a set of input arguments and return an output value. So that might sound a little technical, but at this point, you've already seen functions very often. Nearly every line in R is going to actually have a function. So you might have seen sums or mean or even plus or minus, which are examples of particular types of functions known as operators. So really the basic idea behind a function is that some input goes into the function, some code is run within the function, and then there's some output. In R, if you want to define a function, the syntax is pretty simple. I have an example here. So the main keyword here is, of course, function. To the left of the assignment arrow goes the function name. In this example, it's just function name. And then really the two concepts that change how a function actually works are the arguments and the body. So arguments can include the data you use in the function, so really your inputs, or parameters that change how the function operates. That can just change sort of the code that is run within the function, the way it works, or maybe even the way it's output. And then the body is the actual lines of R code that perform the task and create the function. When you're ready to call the function, it's simple again. You just call function name, and in the parentheses, you have the various arguments that you need to set. In R, you can set as many arguments as you want in a function definition. So let's switch over to RStudio and take a look at a very simple example. We'll start with a function that just adds two numbers together. Obviously, this function is not necessary to define since the plus operator does this, but we'll just use this as an example. So looking at it, we have the parts that we discussed before. So function name is add numbers. We call the function keyword. We tell it will be taking as input X and Y. And then finally, the body is just one simple line where we return X plus Y. So we can run that. And as we can see, now this function is now loaded into R. And we can use a simple example where X equals 3 and Y equals 8. We run that and we get the expected output, which is 11. On this next line, we see the same function defined again, but there's some simple differences right now. In R, you don't need to actually define this return statement. What R will do is it will look at the last line that returns an expression in your R function, and that will just be returned as the output. So we can, if we want to, we can get rid of return. I generally prefer to use return because it just makes it much more obvious where the function ends. And as we'll see later on, sometimes a function can end early and there might be a different return value. Another difference here in this line is that we have omitted the curly brackets. That's because in R, if you were defining just a one-line function, you do not need the brackets if it's just one line. So we'll redefine it, and as expected, we get the same exact output. Now we'll take a look at the different rules for what the function arguments can be. The arguments themselves can be any type. So in the add numbers example, we were using integers, but the arguments can be integers, strings, more complex objects like data frames, or as we'll see later, arguments can also be functions themselves. When you're defining your function, generally data arguments go first. So in our example, that would be X and Y, and then calculation parameters come after. As I mentioned earlier, parameters change the way things operate. That's just a rule of thumb, but it's good to just follow these conventions to make your code clearer to read. We have a few different options for how we can actually specify arguments. So first, the most clear option is by name, where we directly spell out X equals 2 and Y equals 3 in our example. But you can also specify arguments by order. So in our original function definition, it was X then Y. So we can still just call add numbers 2 and 3, and then they'll just be matched up by position. One other way we can do argument matching is through partial matching. What this means is that if we define a function, we'll do add numbers 2 here. The only difference is that we've spelled out longer names for X and Y. And with partial matching, what we can do is instead of typing out the entire X input, we can just put the first few characters. So in this case, we can do X equals 4 or YI equals 10, and that function will still work. However, it's actually recommended that you do not do this. It just makes your code less readable, harder to review, and it's easy to sneak in mistakes. So it's just smart to keep in mind that this is possible, but you should avoid doing it for sure. When we're defining functions, we can also set default values for any of the arguments that we set. So let's take a look in RStudio what we mean by that. Again, we'll go back to the add numbers function, but in the function definition, we're going to do one thing different here. We're going to use Y equals 10 instead of just Y. Now what that does is in our function definition, Y is set to have a default value of 10. What that means is when we call this function, if we don't set a value for Y, the value 10 will be used instead. So let's take a look at add numbers with X equal to 1. We get 11. And as usual, if we want, we can set, we don't have to type out X if we don't want to. We can just use the simpler version. And again, Y is still default 10. Now in this function, we haven't set a default value for X. So what happens in this case, if we try to call add numbers where we set Y but not X, then we'll get an error. And it will tell us argument X is missing with no default. Now when you're setting your default values, you need to take some time to determine which one is the best. Generally, it's smart to choose either the most common value or perhaps the safest value. What I mean by safest is if we do something like sum, where there is a NA value in that function, if we try to sum that vector, we'll get NA. Now that's because the sum function actually has a parameter na.rm, standing for na remove, and its default value is set to false. If we want, we can change it to true. So what's going to happen here is that na will be removed, and now that sum function will return a 3. So the default value is set to false because it's the safest default parameter. Sometimes you'll have an issue in your R code or perhaps in your data, and if you send that to a function like sum, you generally want to know if something has an NA, and if it was set to true automatically, you might easily miss that. So having the default value as false is the safest way to do it. Now that we know a little bit about how functions work and how to create them, we still have the question, why do we use functions and when do we use them? So as you go about writing your code, oftentimes you'll see that you have to do the same operation or particular task multiple times. An easy solution for that is just copying and pasting the code from before. However, eventually that can lead to issues and mistakes. So we can replace copy and paste with functions, and that really improves the readability of our code and the organization, and it makes testing code a lot easier. It also makes peer review much, much easier, and it makes it easier to go back and look at old code if you have to. R for Data Science notes 3 advantages of functions. First, named functions make code easier to understand. Second, updates need to occur in only one place. And third, it helps us avoid small mistakes that occur with copy and paste. So we'll move on and we'll look at an example for exactly what I meant by those advantages. So again, we'll move over to RStudio. In RStudio, we will create a data frame with 2 columns, just random numbers, and we'll take a quick look at what they look like. So as we can see, the numbers range from around -2 to +2. Now, let's say we want to write a function, or we want to change columns A and B so that each one is rescaled between 0 and 1. So in this line of code here, I have a function that does that. All it is it takes the minimum and subtracts it from the column and then divides by the range, so the maximum minus the minimum. And let's create a new column, A1, using that. So as we can see, it works for this one. All the values in A1 are now between 0 and 1. So let's say we want to do that for column B1 as well. What we can do is copy and paste, then go through and make sure that we get each example of column A and replace it with column B. So now we've done that. Let's take a look at what our function results look like now. So as we run it, we immediately notice something here is wrong. B1 does not have all its values between 0 and 1. As we can see, there's a few values that are greater than 1. So you might have already caught it since it's a simple mistake here, but I missed this column reference to A that needed to be to column B. So the reason that happened is because I'm copying and pasting, I'm just going through and changing the columns by hand. It's super easy to just miss a column or a single letter that we need to change. So now we change that, we look at the new results, and there we go. These results are what we expected to see. So that kind of mistake is just one of the many examples where using a function on each column is much better than copying and pasting the code as we did here. So let's scroll down to this next cell, and we're going to write a function called rescale. So as we discussed before, rescale will be the function name, function keyword, X is the only input, and then we define the function with these 2 lines of code here. So first, just to make the code a little cleaner, we will define this range variable and use the range function. And looking in the help, what we can see is that range just returns the minimum and maximum. So it's basically the same exact thing that we've done up here. We just reduced it down to using this already built-in function that we can still pass in the NA remove parameter to, and it just makes it a little bit cleaner. And then finally, we return X minus the minimum as we did above, and then the divided by the maximum minus the minimum. So the code itself looks different, but it's exactly the same process. So let's define that. And now, instead of having to copy and paste all these different lines of code, all we do is just call the same function twice. So we will run that, and now we'll take a look at these new columns. And as we can see, A1 and A2 match, B1 and B2 match. So the function, again, it works exactly the same as the code that we looked up here, but it's just much cleaner. It's easier to use in multiple places, and it's easier to see this rescale function name and then go look right at the function definition. Just much cleaner, much safer to use. Now, naming functions. There's definitely different sort of rules and style guidelines to follow, but all of them hold some of the same recommendations. So first off, names should be short but descriptive, and I have a few different examples here. So as we saw earlier, add numbers is good because it's very clear on what it does. An example of a bad function name is function 1, because it obviously tells us absolutely nothing about what the function actually does. Now the next 2 are bad for other reasons. So this one here is very descriptive, but it's just so long. That will really messy up your code and will just make it look bad and harder to read. And then finally, this last example absolutely tells you nothing. It's way too short. So your names just want to be descriptive. So like we did before, add numbers, rescale, you can immediately have a good idea of what they do. Now, if you create a sort of suite of functions where you have several different functions, but they all work in a same sort of problem or methodology, it's often useful to name your functions using a prefix and then an action. So let's say we have a sort of project where we need to model some data. So after we've trained a model, 2 things that we often have to do are summarize the model and visualize the model. So if we want to write some functions that do that, and we expect them to be used on the same type of model object, then we can use this model prefix. So that way we know whenever we see model underscore and then a verb, we know that it's going to work on the same sort of objects. It's going to be expecting the exact output that we have for it. So that's just another way to make your code convenient and easy to read and easy to review. Finally, as I mentioned before, there are different types of naming styles. So it's up to you to choose the ones that you prefer, but just to use the best practices, you want to stick with a consistent naming style. So add numbers with the underscore here, that's an example of snake case, where you have a word, and then you underscore, and then another word, and it keeps them separate and easy to read. Another example is camel case, where the first word is lowercase, and the second word is uppercase. And then there's also a Pascal case, which is similar, except we also capitalize the first letter. So really, it's just a way to make functions easier to read. And like I said, you can use whichever one you prefer, but you just want to use the same style throughout your entire code. So as I mentioned before, inputs for functions can also be other functions. So we'll look at an example using the apply function. R has an a suite of different apply functions. So there's apply, B apply, L apply, S apply. We're not going to get into the differences right now, but they all work in a similar fashion. And we'll use an example to look at just one example. So let's go here and we will create a data frame, again, just using random numbers. In this case, we'll just take a brief look. We set it so that there's 1,000 rows in each column with just a bunch of random numbers. Now, let's say that we want to take the mean of each column. In other programming languages like C++, for example, it's common to use what are called for loops. So in a for loop, we go through each value in some sort of input that we give it. So in this case, 1 to n column of data gives us a vector of 1 and 2 because it goes from 1 to the number of columns in the data. And then the for loop will loop over each one of those indices. So what we do here is we have created a vector in the prior line, and then within each step in the for loop, we'll calculate the mean of a column. So let's just take a look, for example, column 1, we get 4.499, column 2, we get negative 0.018. Okay, so as we're going through the for loop, the mean of each column gets calculated, and then it gets placed into a slot in the means vector. So let's run that. We'll take a look and we'll get exactly what we expected before. So that's common in other programming languages, but R has built-in options that are much more concise and cleaner to read. And as I said, we're going to use the S apply in this case. So for a data frame, what happens with S apply is it will go through each column in that data frame, and it will apply a function that we specify here to that column in the data frame. So all we have to do is just specify S apply, our data frame here, and then we want to run a function of the mean on each column. And now we look at our results and they are exactly the same as we got before. But the main thing here to notice is that now instead of having all of these lines of code, 4 total lines here, we've actually just moved it down to 1 line. And it's really easy then to just switch out new functions if we want to. For example, we could do something like max. Look at that, it's very easy. Again, all we have to do is just change this one little function parameter. That's it. This is also an example of what is called functional programming, where you map functions over an object rather than allocating out a vector beforehand. This is clean and concise R style code. Okay, so this is the end of section 1, the basics. What you can do here is, once I'm finished speaking, go ahead and pause the presentation and work on these problems amongst yourselves. And once you're ready, then you can press play and move on to the next slide. Okay, let's take a look at the solutions. So for problem 1, we wanted to look at this code without running it in R and figure out what the mistakes are. So for the first part, we can take a look. We're defining a function that squares a number. And if we look at the definition, we use func instead of the function keyword. So if we use function, that will work. Secondly, if we look at the second part of that question, we create a data frame, and then we are writing a function to work on that data frame. Well, let's take a look. we see that we are missing the curly brackets. So if you recall, you don't need to use the curly brackets in R if your function definition is only one line. So if it was just this line, it would work. But since it is two lines, we need to surround these in curly brackets. Taking a look at the second problem, using the following data frame, write a function that returns the data type of each column. Okay, so we can immediately think of the example that we looked at before using the apply function. So let's take a quick look first at what this even looks like. We can look at df2. As we see, the first column is all integers, second column is strings, third column are logical true or false. So R already has a built-in function for determining the type of an object called the type of function. All we have to do then is combine that with what we learned before using the sapply function. And again, as we discussed earlier, the way this works is it goes through each column in this data frame and it runs the function type of. So looking at that and we run it, we get integer, character, and logical. And the nice thing about the sapply function is it returns a named vector. So if we need to remember what the name of each column was, the vector names are right there and they correspond to the column names. Now let's take a look at number 3. Using the following data frame, write a function that returns both mean and standard deviation of each numeric column. Okay, so what we want to do in this case, again, we'll just set seed so we get the same random results every time. Now let's take a look at that data frame. Simple stuff again. Now the complication here is we know we can use sapply to calculate something on each column of a data frame, but how do we use two functions on each column of a data frame? So separately, we could just do the usual like that, but that can only give us one function. So what we can do instead is use the list function. So that returns a list of two objects. Let's do list 1 and 2. And as we expect, we get a list returned. Now we can also name objects in a list. So we can do this. And now we see we get these names back instead of just 1 and 2. So we can combine that with what we already know in the sapply function. So again, we're going to apply to each column in this data frame. But now, instead of just using a simple function like mean, we will define our own function right in line. And the way it will work is just the same as it always is. Whatever function we define here, it will apply to each column. So what we do is we define a function that takes an input x, it calculates the mean of that x and the standard deviation of that x, and it puts them in a named list. And then we can just simply run that and look at that for each column. Again, it returns it named. We get the mean and the standard deviation for both columns. Now, if we wanted to, we could actually define this function outside of apply. And we could do something like mean SD, define it there, then run the function as we've seen before, and we get the same results. The second section that we will go over today is on conditional execution. So what is conditional execution? What does that even mean? So that's just the technical name for something that we're actually used to in our daily lives. So for example, all it is when you change the behavior of something depending on the condition of something. So you might do this all the time. For example, you look up what the weather is going to be outside and you decide what you're going to wear depending on the weather. So in this case, the condition is it cold outside? And then the behavior that changes depending on that condition is if it's cold, well, then you need to wear a jacket. If it's not cold, then we'll wear shorts. So this kind of reasoning is extremely common in all kinds of programming. It occurs whenever you need to make a decision, change some code, or change the output depending on some condition. Conditional execution in R behaves in the same fashion. And the keywords in this case are if and else. The basic structure looks like this. If condition, then we can write code that occurs if condition is true. And then the else means if that condition is not true, if it's false, we'll run the code here. So the else portion is not necessary. You can have just an if clause without an else. In that case, if the condition is true, the code will run. If condition is false, then none of it runs. So an easy example for this kind of condition execution is an absolute value function. So you've seen this before in any of your math classes, where the absolute value returns the value x if x is greater than or equal to 0. And if x is less than 0, we return negative x. So that results in the output always being positive. So to put that in our code is pretty simple. We set x to be the input in the function, and we use an if-else statement. So if x is greater than or equal to 0, we return x, else. So if x is less than 0, because it's the opposite of greater than or equal to 0, we return the negative value of x. So if we run a function like that with the number 2, we'll get 2 out as expected. If we run the function with negative 2, again, we still get positive 2. The way it works for negative 2 is the input, negative 2 will go into the function. It will reach the if condition. Since negative 2 is not greater than or equal to 0, we skip the return x and we go to the else, where we return negative x, and then we get positive 2. Some requirements exist for what we can use in condition. First, condition has to be length 1. Otherwise, we'll get a warning. So what we mean by that is if we use an if function with a vector of booleans, true or false, like this, we'll get a warning. And it will tell us the condition has length greater than 1 and only the first element will be used. So that means if you return something like a true and a false to an if statement, it's only going to look at that very first true. Now that might be an issue, so keep that in mind, and there will be solutions that we'll go over soon for that. Along with that, an error is returned if condition is not a Boolean. The only time that this won't be true is if we put a 0 or a 1. So 0 will mean false and 1 will be the same as using true. So if we look at this example here, if we for some reason put a string in an if, it's going to return an error. However, if we use 1 in the if condition, then that will properly work and it will be seen as true. So in the first example here, we saw that multiple conditions won't work on their own. However, there are options to use multiple conditions. We'll have to use operators and or to do so. And returns true only if all conditions are true, whereas or returns true if any condition is true. So for example, true and false returns false. True or false will return true. Now, if we have a list of Booleans that we need to look at, it's going to be faster than using these operators to use the built-in functions any and all. These work by combining the results that we've seen before. So any is like an or statement, where if there are any trues in a vector of Booleans, it will return true. However, the all function has to have all trues to return true. So if we look at these two examples, running any when there's one true and three false returns true. However, if we run all on those same true and false, then we get false return. So remember, all needs to be all true. There we go. Now, if we want to, sometimes the logic that we need to use for multiple conditions needs to be more complex. So in this case, we can also use parentheses to group multiple sets of conditions. And the true and false will be operated just as parentheses would be in normal mathematical order of operations. So in this case, what will happen is first R will evaluate the true or false, which is, as we know from earlier, that will return true. And then it will return true and true, which returns true. So let's break that down. What we're just talking about. So we have true and true or false. Now that is exactly equivalent. It breaks down and simplifies to true and true. This kind of thing will often be useful for filtering data frames or for filtering vectors. Now, our conditions are not always as simple as just one condition that is either true or false. Sometimes we need to look at cases where there could be multiple conditions that we need to chain together. So let's say we wanted to write a function that returns different output depending on what day of the week it is. So let's say for a weekday, we want it to return workday with a sad face. For a Saturday, we want it to return a fun Saturday. And for a Sunday, we want it to return lazy Sunday. So we can do that by chaining multiple if and else together. And now the way it works is the same logic as before, where R will go through each step consecutively and it will return the step that satisfies the condition. So let's say we define day to be Saturday. The way it will work, it will go through the first if statement. It will check if day is equal to Sunday, which is false. So then it will go to the next statement and it will use the else. Now in this case, we don't want it to end here if it's still not Saturday. We only want it to return fun Saturday if the day is Saturday. So we still need this second if statement here. So going through the chain, it would return fun Saturday. As we can see, that's what we get. Now let's say it is a Monday. Now we can step through. We see day is Monday. It will do the first condition, false. So we move on. We'll look at the second if condition. Again, that's going to be false. So now we get to the next else. It is the final else with no if statement attached to it. So since we've made it there, it is going to return workday with a sad face. If we define that, and as we can see, now we get that. So there's actually no limit in R to the number of if and else that you can chain together. However, chaining together many if and else statements will often make your code very, very difficult to read. So luckily, we have another option known as switch statements. A switch statement is essentially a chained if else, just written more simply. So let's take a look at this next example. What we'll do is we'll define a function that returns a specific operation on X and Y, depending on what the operation parameter is. So in this function, we'll define a function named mathOps. Inputs are X and Y, and then there is an op parameter that can be plus as the default, or it can take on these different values here. So this works just the same as an if-else chained together. So first, let's just run it with the default. We'll do ops equals plus, and what we get, oops, spelled that wrong. We want to use op, not ops, as we defined it. So now we'll run it, and since we use the keyword plus, it will look into the switch statement for op that we feed it. It will match this to plus, and it will return X plus Y. Now let's say we want to divide X by Y. Let's use the divide keyword. And again, we'll follow the different steps. So by setting op to divide, we look through the switch statement, we go down to divide, and we see, as expected, it returns their division. Now there's also a built-in option for if we use an op that is not defined. So let's say logarithm. Now, what we've been able to do using the switch statement is if op is not one of these four here, instead of just returning nothing, we can also have it define an error. So this stop function actually results in R returning an error and ceasing function. And we can also give it a specific message. So in this case, I wanted to indicate that we use an unknown op in the op keyword, and it returns an error. Let's take a look at some common mistakes that we'll often see with conditional executing in R. So we had previously looked at the AND operators and the OR operator. However, there's actually two other types of the same operator. So recall that AND returns true if both are true. So let's take a look just as a reminder. But now there's also the single AND operator. And that actually works in a vectorized fashion. So what this is actually for is if we create two vectors of Booleans, let's see what we get. So what this actually does is it creates the AND operator, but it looks at only the pairwise matches in a set of vectors. So in this example, first it will look at the first position in each vector. So true and true, that returns true. And then it will look at the second position and so on. So for the second position, true and false returns false. Similarly, the single OR operator works the same way. It works on the pairwise comparisons using the same rules as the double OR operator. So a common mistake then is to use the single operators inside an if statement. And as we saw before, what will happen there is we'll get a vector of Booleans, and then we'll get the warning that the condition is greater than length 1 and only the first element will be used. So to avoid that mistake, just remember that if you're using these inside an if statement, you want to use the double operators or functions like any and all because they return only a single value. However, sometimes we do need vectorized ifs and ors, if and else's. So let's take a look at an example. As usual, we'll create a data frame, take a look at it. It's just a random alignment of negative ones and ones. Now, let's say what we want to do is for any negative 1 in this column, we want to replace that with a 0, but leave the ones. That is what if else is for. It is a vectorized function, meaning it works on a vector and it will return a vector. So the way it works for if else is you give it a condition. In this case, the condition is testing if each value in column 1 is a negative 1. And if it is, this is the value that gets returned if true. And then what we can do here then is if it's false, we'll just keep whatever values that are already in column 1. So let's take a quick look now. All of the negative ones have become zeros and the positive ones stay positive 1. The way this works is because if we look at this condition, what it does is it returns a true or a false for each value in that column. Then the if else function goes through each of these values, and if it's a true, it returns a 0 instead. And if it's a false, it will just go back to whatever it was in the original column. This can also often be helpful, for example, if we want to filter a function, let's say, or if we want to filter a data frame. Let's say we want a second data frame, where in this case, perhaps it's only the negative ones. What we can do is wrap this condition inside indexing for the data frame. And now we get only the rows where that condition is true. If else is built into R's base library. But if you use dplyr, for example, in the tidyverse, or if you prefer to use data table, the case when and the f case functions are similar concepts with just a little bit different syntax, and it might be easier to use in some cases, especially when there's multiple cases, but we won't take a look at those right now. Another common mistake when we're using conditional logic and we need to test something is the fact that floating point numbers are sometimes difficult to use with testing equality. So what I mean by this is let's create a variable x that is the square root of 2 squared. So from basic math, we know that x is 2. And our studio even shows that x is 2. However, if we test that, is x equal to 2, for some reason we get false. So obviously something is wrong here. It doesn't make any sense. Now what we can do is let's subtract 2 from x. And again, now we should expect 0. But what we get is an extremely small number. The reason this occurs is just due to the way that R has to store floating point values. This issue is actually common among pretty much every single programming language. It can't perfectly represent all numbers due to the way numbers are stored in memory. So what happens is, rather than actually getting a value of 2 for this function, it's actually 2.0000, many digits of 0, and then this little bit added on at the end. So what happens is R tests only that exactly, whereas there might be this little bit left over. So luckily, there's an all.equal function that we can use, or we can build in our own function. So let's now use all.equal, and we get true as expected. The reason that works is because if we look at the help for all.equal, there is a discussion in the help document about the tolerance. So the default value in this case is 1.5 times 10 to the negative 8. What that means is, rather than testing if the difference between the two numbers is exactly 0, it actually looks at it if the difference is below this tolerance. So what we can do is we can make our own version of this function. We'll define our tolerance to be 1 times 10 to the negative 5. And now what we can do is the absolute value of x minus 2. And that gives us, again, that extremely small number. And we can use conditional logic to see if that difference is less than the tolerance. What we get in this case is, of course, true. So in that way, we can say that, yes, the value of x is equal to 2. Okay, this is the end of the conditional execution section. We'll do some more exercises. And again, as we did last time, go ahead and pause the video and answer these questions amongst yourselves. The first exercise is a classic in computer programming. It's called FizzBuzz. What we want to do is write a function that receives a number as an input. And if the number is divisible by 3 only, print fizz. If it's divisible by 5 only, print buzz. But if it's divisible by both 3 and 5, print FizzBuzz. And if it's divisible by neither, print whatever was input into the function. I've left a hint here. You should use the modulus operator %%. In the second exercise, given the following vector, use if-else to convert any NA to zeros. So go ahead and pause and work on this. Okay, let's take a look at the solutions to these exercises. As usual, we will just jump over to our studio to get a better look at them. So for FizzBuzz, there are many, many ways that we can do this function, but we'll just use a very simple solution. So as I mentioned, the modulus operator was a hint. Now the way this works is if you run a query like this, what it does is it figures out the remainder left over from division. So of course, 10 divided by 3, that gives us 3.33. So we remove the decimal part of it, gives us 3. 3 times 3 then is 9, and 10 minus 9 gives us 1 left over. So really, this function is all about just using the modulus operator as much as we can. So let's define it and we'll take a look at how it works. So let's do fizzbuzz for 11. And we get 11 back. Let's see how it works. So first, we hit the first condition of our if statement. We get 11 modulus 3. That gives us 2. So that this first condition already fails. Now that means that the second condition is not even evaluated because false and true will still return false. So now we jump down to the next condition. We already know that this is false. Now we jump down to the mod 5 condition. That remains 1. So we just print the input 11. Similarly, let's do 15. Now we know that this one should return fizzbuzz, and it does. A nice thing we can do here is, again, as usual, we can use the apply functions. Let's just use 1 to 20, let's say, and fun will be our function fizzbuzz, and we can get the results for every number up to 20. And as expected, we get 1, 2, fizz for 3, 4, buzz for 5, and so on. Now, the second question was, given the following vector, use if else to convert NA to 0. So let's go ahead and create that function. Let me just grab that. There we go. Over to our clean notebook. Let's take a look. Okay, so in this case, we have only one NA, and as we remember, we have the is NA function, and let's look at that, what that returns. So all false except for the one true. So in that case, what that means is for all of this false, we'll just go back to the original vector. For that one true, we'll just go with the 0. And that means in that case, we get the expected results. And that is the section on conditional execution. Moving on to advanced concepts and extras. These go a little bit past the basics, and many of them are just to make more efficient functions or for making functions more helpful in general. So the first thing we'll look at is the ... keyword. What this allows us to do is it can allow us to pass arguments to a function within a function. So as we've seen many times, we use the apply function pretty often, where we apply this function, in this case mean, to each column in data. However, let's say that we wanted to pass additional parameters to mean. How can we do that? That's what the ... is for. Let's take a look. We will set seed again, as usual, create a data frame. This is what our data frame looks like. So let's say we wanted to take the mean of each column. Now, since both columns have NA in them, if we do mean without NA remove, we'll just get NA return. So the ... allows us to do this. We add NA.remove, and rather than it being applied to the sapply function as we usually see, we actually get it applied inside the mean function as such. Now we can also look at the help as usual, and as we can see in the help, ... is shown as third input, and that's why it works with this function. ... also has a second usage. It can also allow us to define functions that can be allowed to take in any number of arguments. So that's very common in the sum function. Let's take a quick look at the help there. This is how it's defined: sum ... and then the na.remove is set to false by default. Now, the way that works, or allows us to work, is instead of having to create a vector when we want the sum of multiple things explicitly, like this, for example, all we have to do is instead just pass it multiple inputs, like such. So these two statements in this case are equivalent. Now, as I've been using pretty often, R also offers several ways to find help and documentation. So one that we've looked at a lot is the question mark. That just brings up the help in RStudio like this. I use it all the time because it's easy to forget the different kinds of parameters or the default values or even the values that are returned. So using the question mark in your function is extremely helpful. That is also the same as just using the help function. Again, it returns the same thing over here. Now, let's say you don't know exactly what function you want, but you have an idea. Perhaps we want to check out something for regression. We can use double question mark in that case. And then what will happen is R will search a bunch of different libraries that you have in your loaded session. So it will search the R documentation for a word or a phrase. So in this case, we search for regression, and these results show us many different possible matches. I don't use this one as often because generally I'll just use Google to find the result faster. But again, it's nice to have this functionality, and it's pretty easy to use. And then you can just follow the links to whatever you are looking for. Anonymous functions are a new feature in R 4.1, and really it doesn't change that much. It just makes some syntax a little bit simpler. So instead of writing out function X, we can just use this /x. So using the prior data frame that we already loaded, what we can do, let's say again, we want to calculate the mean on each column. We'll use sapply as usual. And again, for this example, where the data frame has NAs, we need to somehow specify that NA should be removed to get actual values. So instead of typing out function, we can use the exact same syntax and just use the anonymous function slash as such. Now again, we get these NAs back. The nice thing is we can use function definitions and we can still use the ... operator. So in that case, all we have to do is in our function definition, leave a slot for ... pass the ... to the function within the function. And then we can still just specify na.remove outside of the function and the sapply, and it just makes it a little bit cleaner and simpler to read. So we've already seen some instances where using the wrong type can result in errors. R allows us to do a few different things to restrict arguments, whether we want the arguments to be of a particular type or restrict the values that arguments could be. So if we go back to our add numbers example, obviously this makes no sense, but we can do x plus y, and 2 plus string doesn't mean anything. So what we get is an error saying error in x plus y, non-numeric argument, which is the string portion, to a binary operator. So in R, it expects both of these values to be numeric. So let's say we wanted to actually put in some sort of checking system to make sure that X and Y are both numeric. And we can do that, of course, using if statements. So let's define a second version of add numbers. And instead of just using the built-in error system in R, we'll define our own. So what we'll do is we'll check that both X and Y are numeric. We can do that with the isNumeric function. So let's do that, see what it looks like. IsNumeric on 1, true. If we actually send a string instead, we get false. So what we're doing here is within the parentheses, we are checking that both X and Y are numeric. Now, what this exclamation point means is it's negation for that. So let's do this. Let's define X to be 2, Y to be 3. Okay. And let's do the condition. It returns true as expected. Now, what negate does is it flips that around to false. The exclamation point means take the opposite. So exactly. So instead of getting true, now we get false. The reason we do that is because we need both of these to be numeric. And if they're not both numeric, then there must be an error. So now that this returns false, if we pass a string, so now let's change Y to string again. Let's take a look at that, what that returns. So again, inside the parentheses is false. Now, negating that returns true, meaning this line condition is true. The if statement triggers, and we get our own personal error message. And in this case, we just remind the user that X and Y must be numeric. So now let's actually define that function. Let's use it, and we have our own error code. So sometimes it will be enough to just use the built-in error codes that R has, but other times we might want to define our own to make it more clear or more helpful. Similarly, there's also the stop if not function. So what that is, now let's take a look at the documentation. If any of the expressions in ... or expressions are not all true, so we've seen it all before, stop is called. So this just makes it a little simpler to write out, because instead of having to combine the error conditions and then using negate, all it does is it looks through each part in ... or expressions. So it goes through this one. In this case, X is true. However, Y is not numeric. So basically, because using the all function on this returns false, this stop is triggered. The error message will be a little bit different in this case. Instead, it will just look at which one was not true, and it will tell us exactly that. So in this case, is.numeric Y is not true, so the function is stopped. Now there is another option that we can use. In this case, it is the match.arg function. So let's go back to our math ops function from before, except we'll just make it a little bit simpler this time. Now what we'll do is previously we set op to be plus by default. We're going to change up the definition here just a little bit, and instead what we're going to do is define the valid options. So we'll say that op can only be one of plus or minus. And then we're going to pass that op to the match.arg function. Now let's see what happens when we actually run this. So since we're passing in minus in this case, which is matched to the minus in the definition, it will still work, and it will return 3 minus 2. Now let's run math ops, but using the logarithm op. So again, what it will do is it will check if op, using the match.arg function, it will check if logarithm is in this plus minus. Obviously it's not, so an error will return. So these are just all different options to do basically the same thing. Really, it comes down to convenience, simplicity. You can use whichever method fits best with your code to keep it clean and keep it readable. Now, the next concept are called infix functions. So almost everything we've seen so far are prefix functions. The name of the function comes first before the arguments. So pre meaning before. For example, sum of x and y is prefixed because the function sum comes before the arguments x and y. Now R also has some functions that are called infix functions. The operators are examples of these because the operator comes between the arguments. So x plus y, that's an infix because the operator plus is between the x and y. We can also define our own infix functions and call them using the percents. Now let's take a look in RStudio at what that means exactly. So when we're defining them, what we want to do is the actual name will go in between two percentages. And we also have to use the backticks, the button at the top left of your keyboard, like that. That's how we define them. So we'll take an example from the data table package, particularly the in function. This is definitely one of my favorite functions. What it does is it allows us to check if a value is in a vector. So the way it works is we'll define it and we'll step through it. So x is the value that we want to check if it's in the table vector. So what it does, it will then use the match function. So let's check if the letter A is in the vector ABC. So what that does is it returns the number 1 because that means it's in the first position. So then all that the in function does is if it checks if that value is greater than 0 because we've specified the no match to be 0. So what that means is, let's take a look. We'll check for D. And because we haven't specified no match, that returns an NA. So now if we do no match 0, using the L just means it's a particular type. It doesn't matter that much for our case right now. So now instead of returning NA, it returns 0. So again, now what happens if we add greater than 0L is it just turns this into a Boolean. So because match in this case returns 1, that's greater than 0, returns true. In the case where we're looking for D, that returns false. Now we could similarly write this just using the isNA function. So that returns true, or pardon me, that returns false, because matching A and the vector does not return an A, and then we can negate it. So there's just different options for writing this. So now what we can do is we define our function, and instead of writing sometimes ugly code, or at least just less clear code as the above, we can use this really nice infix operator for in. And now what we get is true. This one is especially nice using it to filter data frames, for example, because again, it's just such clean code that we can really easily write that and read it later on. Another concept that we'll look at now is called generic functions and dispatch methods. Now, the names themselves aren't that important here. The concept is we're going to create a function with the same name, but it actually does something different based on the data type. So let's take an example. Let's look at the number of elements in a vector or a data frame. So for a vector, the number of elements is just the length. However, for a data frame, the number of elements is the number of rows times the number of columns. So the concept is exactly the same essentially, but the actual calculation is different. So of course, one option would be to write a function that uses an if statement, and if we return length, if it's a vector, otherwise we return rows times columns if it's a data frame. Another option, sometimes cleaner, is to use generic functions with dispatch methods. So the way this works is we first define this generic function. So let's call it the number of elements. And all we tell it to do is use method number of elements. So far we actually haven't created a real function that can do anything yet. The real trick occurs because now what we do, we'll define the number of elements function for type numeric. So again, something like this. That gives us a double, and we can also look at is numeric, returns true. So it will work for that kind of thing. We define this function to just be the length, and then we can define a second function with the same exact name, except we just change the suffix here. So now what we're doing when we name them like this is if we call it on the particular type that we define, it will go to this function first. It will see this use method. Then it will match the input X to whatever we define the different possibilities to be. So now when it's a data frame, we define it to be number of rows times number of columns. So we'll test this first on a vector, as we've seen, is a numeric type. So what we get is length 2. Now let's do this on a data frame. As expected, what would happen is we can do this, of course. That returns 4 because the data frame, of course, has 4 different values. But now we just call the function, and again, we get 4 as expected. So we're able to call just the same name, number of elements, and internally, R will look at the use method. It will find this name, then it will match it to the data type. So again, we could use an if statement within a function, but this just makes it much cleaner. It's really easy to define, and you can define whatever behavior you want based on the input type. The next concept is the environment. So first we'll go through R in a nutshell for the exact definition, and then we'll look at what that actually means in practice. So the definition is an environment is an R object that contains the set of symbols available in a given context, the objects associated with those symbols, and a pointer to a parent environment. So when we're actually working in R, the concept environment is made very simple when we're using RStudio because it nicely actually outputs what's in our current environment. So really, an environment is basically just the sort of sandbox that you're working in. Whenever we define either a value or a function, it goes into the environment. Now, this consideration becomes important when we're working with functions. Real quickly though, let's say we define a value x, those we already have. We see that it's in the environment. What we can do if we really need to is we can remove x from the environment, and now it's gone. If we try to call x, we'll get this error because object is not found, it's gone. So how does this apply to environments within functions? Well, what happens is if you create a function and you run a function, a new environment is created within the original parent environment. So right now we have one environment working. It's where we have defined everything so far. But let's define a new function. First, let's remove y because I believe it's still in there from earlier. Yes, so we'll remove y. So it's gone. Now let's run this power function. And as expected, it returns an error because the object y is gone. The reason why is because first, R will look in the function environment for the value y. It's not there. Then it will look in the parent environment for the value y. And if it's there, it will work. Otherwise, it will keep looking up and up and up until it finds it or it doesn't find it. So what we can do is now we define y. And now we can run that power function. We get 3 squared. So again, what happened here is first R will look in the function environment. It will look for y. It doesn't find it. Then it will look in the next environment up, which happens to be the global parent environment, and it finds that we've defined y, so it will use y assigned 2. Now let's see what happens if instead we define y in both the parent environment and the function environment. Before I click this, what do you think is going to happen? Well, it's going to run and we'll get 27. So what happened here is since we're in the function environment, it first looks there. So even though y is defined first in the parent environment to be 2, the scope of the function first looks within itself to find y assigned to 3. And therefore, y is used as 3 in the function. So when you're programming a script in R, you have to keep environment in mind. Sometimes you can make mistakes and accidentally use a value from your parent environment when you mean to define a new one. You just have to be careful since R allows globally defined variables to be used within local functions. So just keep that in mind and make sure you're careful when using it. One last reminder is to clear your environment every time before you run a script. So in RStudio, that's very easy. We can just use the broom above the environment to completely remove everything. So what that does is, as we saw before, we can do remove y. RStudio will just automatically go through and remove every single one of our functions and our data and our values that we've defined so far. You want to make sure you do that before you run any R script, because if you define something, forget to clean it, you might forget that when running the script, it's a different value, and your results might be wrong. Another really important concept is the concept of reproducibility. You should basically be able to run every single script in R just completely through without having to do anything yourself. And if you forget to clear the environment, you can actually forget that you've set variables yourself. So a function that shouldn't run can still run. And again, it's just safer to clear out your environment before running it. Now, one thing that this does not clear out are loaded libraries. If you want to clear out a library that you've loaded, you have to completely restart your R session. Finally, the last concept we'll go over, but probably one of the most important, is documentation. Documentation is extremely important for both you and your coworkers. All you really need to do is include a basic description of the function, the inputs, and the outputs. This is just so important so that others who are reviewing your work can easily know what they're doing without having to go through each line step by step. And even for yourself, because as I've mentioned before, sometimes you'll have to go back to code from months or even years ago. And if you see a function, you might not immediately know what it does. So writing documentation will just make the process so much simpler. So a really simple way to do it is just to define this within your function. So in this case, we go back to our add numbers function. We say what it does. It adds two numbers together. That's the concept. The inputs expected to be X and Y, and they're both expected to be numeric. And finally, the output is again numeric, and it's just the sum of X and Y. So if a new colleague or something needs to read your functions, they go to this function, they see exactly what it does, what it needs, what it returns. If you need to use more complex documentation, one example library would be the R-Oxygen2 library. That can even help you with creating the manuals if you need them. So now we're on to the exercises again. The first will be rewrite the math ops function from the restricted argument slide so that there is a new option for logarithm where we use log of X with the base Y. But on top of that, I want you to include code to restrict X and Y to be positive values only if logarithm is chosen. And then finally, write an infix function to remove an element from a vector. Go ahead and pause the video and continue once you're ready. Okay, let's take a look at the solutions to the exercises. For number one, we are rewriting the math ops function to allow for logarithm, and we're also including code to restrict X and Y to be positive values when we choose logarithm. So let's take a look. Now I've combined a few concepts that we've gone over. First, we'll use op, and we'll set the allowed values along with the match.arg function to force the values to be within these three. We'll use switch again, and then we'll use a little trick along with logarithm and the stop if not function. So what we've seen so far before this was each function in the switch, within the switch function, was only one line. So we could just define it right in line. Now what we'll do is we'll add the type and value checking within just one function for logarithm. So what we'll do is we'll wrap that in curly brackets. So in the case that we choose logarithm, it now will also use the stop if not function to make sure that X and Y are both greater than 0. And if they are, then it will use log of X and Y. So we keep this within just logarithm because we want to allow negative values for plus and minus, but we have to return an error if it is logarithm. So now let's test it out. Let's define it. We'll test it out. And as we would expect for log of 2 with base 3, we get 0.63. Now let's run it with a negative value. And as expected, we get the error that Y greater than 0 is not true. And just to test things out, we'll make sure we can still use the other options. And it works. So this is a pretty simple solution, but there are definitely many others you could have gone with. Now let's take a look at number 2, where we'll write an infix function to remove an element from a vector. So this is definitely something that comes up often in code, is you have to remove something from a vector. So again, we can use a nice, convenient infix function that will make the code very readable. And what we'll do is we'll define an infix function titled rem, and all we'll do is we feed it the element that we want to remove, the vector to remove it from, and then the code itself is simple. It uses a condition again. To first, it will look at the vector and it will check if any elements are not equal to the element that we want to remove. So let's take an example here. Let's do that. 1, 2, 3. Now we've got 1, 2, 3, and let's say we want to remove all the values not equal to 2, so saying we want to remove 2 essentially. So what that means, now we can use the not equal to operator to look at that, and again we'll get a vector of true and false back, and then we use that as indices within that vector. So now we do this and we say we only want to keep the indices that are true, and we get that back. So now just using the infix function, we can very clearly and concisely write a function where we're saying we want to remove 2 from the vector 1, 2, 3. And of course, we forgot to define it first. So now we actually run it. This time it will work. And with that, we've actually reached the end of our presentation. And in conclusion, the key takeaway is just to remember to use functions whenever you can. Use them whenever it will make your code cleaner to read, to write, and easier to review. And just follow the basic steps that we've gone over so far in this presentation. Thank you so much for joining me today, and I hope that my presentation has been helpful, and good luck with the rest of your learning. Thank you so much.